And welcome to the Wednesday noontime seminar series at SETI Institute. As is a standard with these seminars, we ask that you hold your questions until the end if you can, because the seminars are being recorded and they will show up on YouTube and also on the SETI.org website in a few days where you can listen to them again at your leisure. Today we have the privilege of having as our speaker Dr. Risa Wechsler from Stanford University. She's an assistant professor there in the physics department and also in the Department of Particle and Particle Astrophysics at the Stanford Linear Accelerator. She's also a member of the Kavli Institute for Particle Astrophysics and Cosmology. Risa got her start in physics at MIT and then went on to get a PhD at the University of California at Santa Cruz, where her dissertation was called Dark Halo Merging and Galaxy Formation. After that, she did a postdoc at the University of Michigan in the physics department, and then went on to work at the University of Chicago in a few fellowship roles, first as a Hubble Fellow, and then as an Enrico Fermi Fellow, and then as a Kavli Institute Fellow, before moving to Stanford, where she I think, arrived in 2006. She has a fantastic website, as I've mentioned to her, and it has a lot of sort of shared outreach activities where she actually has mounted her presentations from various public lectures and academic lectures, and I would encourage you to have a look if you're interested. And among her broad research interests include galaxy formation and the development of structure of the universe, evolution of galaxy properties as a function of time and the environment, and the long-term dynamics of the universe, and also extracting cosmology and galaxy formation parameters from large galaxy surveys. She's a member of various ongoing astronomy surveys today. She's also interested in the nature of dark matter and dark energy. And I think she's also a dancer, but that's something you'll have to ask her about after the seminar. So without further ado, I'll hand it over to Risa, and today she's going to talk about connecting galaxies, halos, and star formation rates across cosmic time. Thank you.
Thanks very much. I think this,
I should sort of keep this.
Okay, great. It's a pleasure to be here. And as my title may indicate to you, I'm going to try to cover the entire history of the universe and all of its contents in the next hour or so. So got a lot of ground to cover. Just to calibrate, how many of you are some sort of astronomer or planetary scientist? Okay, good. I just wanted to get some idea to calibrate. I'll try to reach the whole audience here. So the two pictures that, and actually one more calibration question. How many of you know what I mean by a halo? Awesome. Okay. Okay. So the two pictures that I'm showing here are the deepest picture ever taken of the universe by the Hubble Space Telescope, called the Hubble Ultra Deep Field. And one of the largest numerical simulations ever performed, actually just completed a few months ago, was done down the road at NASA Ames by some collaborators. And this is one of the simulations that we'll be working with in the next year or two. And my main topic is basically about how we understand the left half of the picture from the kinds of simulations that I'm showing on the right. Okay, so that's what I'm going to try to sketch out for you today. So just looking at this picture in a little bit more detail, because it's just so totally awesome. Right, this shows you galaxies all the way from, very, very nearby to essentially 13, even a little more than 13 billion years in the past. So it's a very, very tiny piece of sky, but we can see almost the entire history of the universe, at least its light output in the optical in this image. So this is one of the things that we want to try to understand with our theories of galaxy formation and structure formation in the universe. Okay. We can look in a little bit more detail at galaxies in the local universe. This is a composite picture of galaxies detected in the Sloan Digital Sky Survey, which is to date the largest galaxy survey ever performed. There are many other larger ones that are in the planning stages, but this one has essentially just completed, just had its essentially final data release. And what this plot shows is a diagram of galaxies as a function of their magnitude. So this is luminosity, brighter galaxies on this side, dimmer galaxies on this side, versus their color, right? Redder galaxies here, bluer galaxies here. And this is essentially a measure of the age of the stars, the average age of the stars in the galaxies. So the galaxies with older stars are up here, and with younger stars are up here. And what you see, a few things that you can see from this diagram is that these various properties of galaxies are correlated. So we see on this side of the diagram big, bright red galaxies with old stars, mostly elliptical in shape. And we see on this side of the galaxy small, dim blue galaxies that are currently star-forming, typically disk galaxies. And the main thing here is that all parts of this diagram are actually not populated. There are no galaxies over here. None of the very, very brightest galaxies are blue, and none of the galaxies over here are very small. So all of these properties are tightly correlated. So that's one of the things we want to try to understand about galaxy formation. But many galaxies also have sort of bimodal properties. So we sort of have two populations of galaxies, red galaxies and blue galaxies. And as I showed you in the previous plot, those things are actually correlated with lots of other properties. So this plot shows, for example, how the brightness of a galaxy is correlated with its color. You see there's basically two sequences, this so-called red sequence, and then this one's usually called the blue cloud. You can see the red sequence is a lot tighter than the blue cloud. Okay, so this is one of the other things we want to understand. Another sort of observational fact about galaxies is that galaxy properties are strongly dependent on environment. So galaxies in the richest environments where there's lots of other galaxies around, in galaxy clusters, for example, this is a picture of one of the most massive galaxy clusters, also a picture with the ACS camera on Hubble Space Telescope. You can see that these galaxies all actually look very similar. They're all sort of these big round blobby galaxies, very different than sort of your typical galaxy, which is in this image of the field. And of course, typical galaxy in this image is actually not nearby. It's much further away, and so you're actually observing those galaxies at much earlier times. Okay, so one of the things we can do to understand these things is to look on very, very large scales. So it turns out the universe is extremely clumpy. And this is a picture of the galaxy distribution over the entire sky in the local universe. This particular image is from the 2MASS survey, which surveyed galaxies in the infrared fairly nearby, but out to redshift of about 0.1. Okay? And so you can see that the galaxy distribution is very, very clumpy. There's lots of filaments, tight structures, lots of interesting things. We, of course, can't see the plane of the Milky Way, so that's what's shown there. Okay, so how did this plot, how did we get to have this very clumpy distribution of galaxies in the local universe? Well, let's go back about 13.5 billion years and look at what the clumpy universe looked like just a little bit after the Big Bang. So this is what the universe looked like about 400,000 years after the Big Bang. This is as observed by the WMAP satellite, which observes the cosmic microwave background. So what it's looking at is temperature fluctuations in the early universe. The specific reason that we get to see this 380,000 years after the Big Bang is because that's when basically atoms can form, and from that time photons can free stream towards us. Before that, it's basically just too crowded for photons to get anywhere. After that time, the photons can travel directly to us. Now, this looks pretty clumpy, but it turns out that this picture actually has the contrast blown up by 6 orders of magnitude. And so this is actually, these clumps are actually 1 part in 100,000. Okay? If you had not blown this up, it would look completely smooth 2.7 degrees in every direction. And so these are just these tiny, tiny fluctuations. And so the main process that I study is how we get from these tiny fluctuations to the clumpy universe that we see today. So this picture is sort of iconic for a couple of different reasons. One is because it tells us about these initial density fluctuations. And the other is because by looking at these various fluctuations and on what scales they are and how large they are, you can actually tell what the universe is made of. Okay? So this is what the universe is made of. This is a really amazing picture for a number of reasons. One is that 10 years ago, we didn't know the answer to this question. Okay? When I started graduate school, we were running cosmological simulations with all kinds of various properties here. We really didn't know. And now these numbers are known at at least the 5% level, depends on which number you pick. Okay? So this is pretty cool. The other thing that's really phenomenal about this picture is that even though we know what these numbers are, you can see there's basically three major pieces. One is everything in the standard model particle physics, everything on the periodic table, that's all in this 4%. Okay, then the rest of the matter is so-called dark matter. It's something that is not one of the standard particles. We do think it's a particle. We don't know what that particle is, but we can observe its effects gravitationally, both on small scales and in the total dynamics of the universe. And then the third major piece is this thing called dark energy, which we really know even less about. The main thing we know about this component is that it's currently accelerating the universe. So we have this situation where we can sort of write down what these various pieces are, but 95% of it is stuff that we really don't understand all that well. Okay, so and it's worth pointing out that of this 4%, most of that is actually hydrogen gas, some helium gas, and a really tiny fraction, only a tenth of that, is in stars. Okay, so this is just showing one plot that shows the current constraints on the two parameters that basically specify these numbers here, the 22% and the 74%, which basically are the amount of dark matter and dark energy. Okay, this is a plot by my colleague Steve Allen at Stanford and his collaborators, but also combining results from the cosmic microwave background, supernovae, their work on clusters, and there are many other constraints that go into this. Actually, these three are just a few of them. There are, at least 20 different observations of different things with different systematics that point towards this basic picture. But just to summarize, basically, we know what dark matter does, and I'll tell you in the rest of the talk how precisely we actually do know that. And we know how much there is, but we don't know very much about what exactly it is, what particle it is. This piece, we know that something is accelerating the universe, and we know how much it contributes to the total density. But that's about it. We don't know what causes it. We don't know what might have started it or stopped it. We don't really know how it's distributed, although it has to be fairly smooth. And this piece is actually quite interesting. We know what the baryons are, right? We know what stars are made of. We know what the gas is made of. But it turns out that their behavior and evolution actually requires, understanding complex physical interactions on a huge range of scales, from parsecs to gigaparsecs. Okay, so it's 9 orders of magnitude in size, and then many more in volume, right? That we have to be able to understand the interactions of baryons, and so this piece is actually, in some ways, the most complicated to actually make detailed physical predictions for. Okay, so that's actually a lot of what I'll be talking about today. So just to give you the general picture here of the timeline of the universe, right? We think there is some process that happened before that cosmic microwave background observation, probably in the first 10 to the minus 34 seconds. The best candidate process is something called inflation, right, which generates these fluctuations on a wide range of scales. We think these fluctuations are basically Gaussian. They get set in the initial density field at this very, very early time. we then measure through the CMB exactly what those density fluctuations look like on different scales. And then from 400,000 years to the present, those fluctuations are being amplified by gravity over this entire time to produce this kind of picture. And the gas, which is sort of initially evenly distributed with dark matter in the universe, radiates and cools and sinks to the center of potential wells and forms stars, which we then observe as galaxies. Okay. So in this picture, there are sort of two very fundamental problems that drive my own research. One is, how do galaxies form, right? How do we understand all of that complex astrophysics? And because most of the mass in the universe is dark, right, 85% of the mass in the universe is dark, that means that understanding the evolution of the dark matter structure is really sort of the underlying framework that we need to be able to understand galaxy formation. And so that's the first thing that I'm going to talk to you about. And then the second sort of fundamental problem is, what is all this dark stuff? And in my own work, I'm particularly interested in how can we use galaxies, large survey observations and detailed observations of individual galaxies, to probe the dark side, to probe how structure forms, what this dark energy might be, what are the properties of dark matter. Okay, and the key piece of the puzzle really for answering both of these questions is, how is the mass in the universe connected to the light in the universe? Okay, and so that's going to be the main topic of my talk. So the first step in this piece is to understand how the mass distribution evolves. Okay, and that's a very difficult question to answer observationally. It's not totally impossible because we can get some handle on this from gravitational lensing. But it's an easier question to answer with the theory. Okay, and it turns out that as physics problems go, this is actually a conceptually simple one, although it's computationally challenging. And it's conceptually simple because we basically know the initial conditions, and we know what the basic physics are. So the initial conditions are what I've essentially already shown you. Right? What this plot tells me is, what are the density fluctuations in the universe on various scales? Okay? And I know what the basic physics is. The basic physics is just gravity. Right? Just gravity. So I take these initial conditions, and I turn on gravity, and I put this in a very big computer. This is the computer we have at SLAC. And the reason we need a very big computer is because this is a nonlinear problem. Okay? You can see that these fluctuations are pretty small. The fluctuations that I showed you on my first slide, and as I'll show you in the upcoming slides, are quite a bit bigger. And it's something that you can't just write down with pen and paper how these things work out. So you need a very big computer. The state of the art with the simulations that we're doing now is that we simulate 5 to 10 billion particles. Okay, so what we do is we break the total mass density in the universe up into lots of little pieces. It's called an n-body simulation because we assume all those particles are the same, have the same mass, and then we just see what happens. Right? Okay, so let's look at an example of this. This is an example from the Millennium simulation performed in Garching. And I'm going to step through in Redshift. I'm going to show two scales of the same simulation. So this piece in the corner here is just a zoom in of this central region. Okay? So this is in the fairly early universe, Redshift 18. For those of you who don't think in Redshift, the rule of thumb is basically that the size of the universe is 1 over 1 plus z. So the size of the universe at Redshift of 18 was 1/19 the size that it is today. Okay? This is now at Redshift 6 that you can actually see that quite a bit has already happened between Redshift 18 and Redshift 6. And this is still less than about 1 billion years after the Big Bang. You can see there's already quite a bit of structure, especially in these particularly dense regions. Here's now Redshift 1.5. You can see it's much more clustered, lots of very tight, dense regions. And this scale here is a gigaparsec, basically, this scale here. That's, depending on how you count, somewhere between a third and a tenth of the total size of the universe. Okay, now we have redshift 0, and you can see that there's even more structure, but actually a lot of the action happened at fairly early times. Okay, so we can do these simulations on a wide range of scales. Right? It turns out that, because we're limited by computational power, and actually the biggest limitation is memory, because we're talking about, how many particles can you fit in the simulation, you can't simulate everything you want to at once, so we basically do these simulations on various scales. These 4 are from a large suite of dark matter simulations that some colleagues and I have recently been doing. This goes from about 2 gigaparsecs down to 400 megaparsecs. This is about half the size of that, so 250 megaparsecs. Okay, so for calibration, right, a large cluster in the local universe is about 1 megaparsec, and this is about 250. Okay, so this is the simulation that I just mentioned to you, very, very high resolution simulation. Now, how this process happens depends on the initial conditions, right? It depends on what is the total amount of stuff in the universe, and how that stuff evolves, right? So this is just an example of how this universe proceeds in 3 different cosmological models. Unfortunately now, no one does these very, very high resolution simulations anymore of these very different models. And the simulations people do now, the parameters are so tight that you can't actually see the difference. But so these are substantially lower resolution. These are from simulations about 10 years ago when we didn't know the answer. But one thing you can see is that if all of the energy density was in matter, the evolution would happen a lot more quickly than the situation that we live in. Our universe is closer to this one called lambda CDM. That lambda stands for the cosmological constant, this dark energy piece. C stands for cold dark matter. C stands for cold, and the DM is dark matter. Right? So you can see that there's a big difference, right, between how the universe evolves depending on how much matter it has. Okay, so let's look now in a little bit more detail. This is a movie of one of these very, very high resolution simulations. This is now a much smaller scale. This is 40 megaparsecs, so much smaller than the smallest one I showed you earlier. This simulation was actually also, the visualization was actually also done at NASA Ames, and we're going there tomorrow to talk to them about doing our new one. So you can see lots of things. The countdown here is gigayears from now. So we're now looking at 6 gigayears in the past. And you can see that all of these very dense knots are forming. This, again, is just a simulation of dark matter. But we expect that galaxies live at sort of every peak in this dark matter distribution, as I'll explain in a few moments. So lots of interesting structure there. So the basic picture, right, is we've got these density perturbations in the early universe, small density perturbations. We've got cosmological expansion. That was scaled out of the movie that I showed you. That was a co-moving volume, so I had scaled out the expansion. But in general, you basically have this tug of war between the expansion of the universe and gravity pulling the regions that started out a little bit denser together. And in the regions where gravity wins, you basically get these dark matter, gravitationally bound dark matter structures called dark matter halos. Okay. So what is a halo? So now I'm zooming in on this simulation a few more orders of magnitude to zoom in on an individual dark matter halo. And here I've just drawn circles to indicate what we call a halo in such a simulation. And it's not as simple as you might think, because you can see that there's lots of substructure. Right? The structure continues all the way from very, very large scales to very, very small scales. So within a gravitationally bound region, there are also lots of little bound clumps, and those we call subhalos. Okay? So schematically, when we say halo, we just mean something that's basically a gravitationally bound object. Operationally, what you do is you go into your simulation and you define density peaks. Okay? And within a given density peak, you're still going to have bound objects, and those are what we call subhalos or satellite halos. Okay? So in a universe dominated by cold dark matter, small things form first and then merge and grow to become larger things. This is a movie of that process, just looking at the formation of a giant cluster halo. Now this counter is redshift, so this is about 7 billion years ago. You can see lots of little things coming in. It's a pretty messy process, lots of substructure, a big merger a few billion years ago forms a very massive cluster. This plot on the left here showing time going down just sort of schematically illustrates this process. This is from my thesis where I studied the statistics of this process for a large sample of halos. But the basic thing to get out of this picture is that for a typical dark matter halo today, that was built up from the mergers of lots of very small objects at early times. Okay, so all of those mergers happen to build what we see today. So here's a one-slide version of all of galaxy formation. Okay, so the basic picture is that in the early universe, dark matter and gas started out well mixed, right? In that picture that you see with the CMB, the density fluctuations were of both the dark matter and the gas. They had the same density fluctuations. They were both very small. And as those fluctuations grow, where the density is high, the gas can cool and sink to the center of these dark matter halos. And right, the key difference between dark matter and gas is that gas radiates, so it sinks to the center. Dark matter doesn't interact with electromagnetism, so it doesn't radiate. And so you get this object where the dark matter is in virial equilibrium with the kinetic energy of the particles supporting it against gravity. And for the gas is in pressure equilibrium with the pressure force of the gas counteracting gravity. And so this is sort of your schematic picture of galaxy formation. And we expect basically that every dark matter halo that's massive enough so that gas can cool should basically get a galaxy at its center. Okay, so that's the basic picture. So that's pretty simple, and there's lots more complicated galaxy formation modeling, and I just have one slide to outline the two primary approaches to the way people do galaxy formation modeling. So one way is you basically try to put all of the physics that you know directly into your numerical simulation. So we talked already about the gravity piece. You also can put in basically the hydrodynamics of the gas so that you simulate the heating and cooling. Now, you can't do this at high enough resolution to actually simultaneously simulate star formation on the relevant scale and the cosmological evolution that we've talked about. So typically people put in what they call subgrid physics models, basically prescriptions for how star formation occurs based on the density of gas, and prescriptions for so-called feedback, which is basically energy input into the gas from various physical processes like supernovae, AGN. All of these things can basically heat up the gas for various reasons. And there's been tons of recent progress on this. I was at a meeting last week where I was just blown away by the sort of the scale at which people are now doing this. Resolution has increased phenomenally, but it's very computationally expensive. There's still lots of physics we don't understand. And basically, none of these simulations are really getting the right answer yet. Whoops. All right. Another approach is to basically say, well, it's hard to simulate the whole thing, and so I'm going to have some prescriptions for the pieces of the physics that I can't simulate. So the gas cooling, the star formation, the feedback, all of these things. And that's done sort of on the framework of these merging dark matter halos that I described to you. Typically, that's called semi-analytic modeling. And that's been a very valuable approach. There's some issues, right? One is that there's lots of free parameters. You basically have to write down some prescriptions. You don't necessarily know. Some of them are physically motivated. Some of them are observationally motivated. But there's a lot of uncertainty. And you may miss some of the important physics. So the other way, and the approach that I'm going to talk about now for the rest of the talk, is a more empirical approach to take the piece of the physics that we really understand, which is the structure formation, and then take the rest from observations and try to infer what is the connection between these two. Okay? So I've already told you how successfully we can simulate the distribution of matter in the universe. And now with very large surveys, we can observe the distribution of light. Okay? So the basic idea that I'm going to talk to you about is basically the following, right? We basically know, given the initial conditions of lambda CDM, which are now fairly well pinned down, we can simulate how that mass assembles, how structure forms, how dark matter halos assemble over time, how they cluster, how many of them there are of various masses. This piece is actually now very well understood. And then the observational piece, we have basically statistically well measured populations at various epochs. Very well measured in the local universe from surveys like Sloan. Slightly less well measured, but still pretty good at redshift of 1. The biggest survey there is called the Deep Survey, performed also Bay Area survey, Santa Cruz and Berkeley, largely. And with much larger error bars, there are actually constraints on the galaxy population, even back to redshift 3 and 4, and at the very massive end, even to redshift 7, where there's been sort of a few tens of galaxies detected, very massive galaxies at redshift 7. Okay, so the idea then is to use these two pieces of information to get a constraint on how galaxies and halos are connected at given epoch, right? At redshift 0, at higher redshifts, and then to use what we know about how dark matter halos grow over time to infer how galaxies grow and form stars over time. Okay? And what I'm going to try to tell you is that despite the sort of enormous complexity of galaxy formation and all the physical processes that go into it, actually many, if not most, of the basic trends of galaxy formation can be understood by this very simple framework, where actually the properties of galaxies are largely determined by the mass of their dark matter halo. Okay? And to 0th order, galaxies are actually a one-dimensional family that's set by that mass and the star formation history that's implied by that mass accretion history. Okay, so let's just look a little bit more at some of these galaxy properties. So first question is, how many galaxies are there as a function of some property? So what I'm showing on the left here is the galaxy luminosity function. This is now exquisitely well measured from the Sloan Digital Sky Survey in the local universe. This plot's actually a few years old, so the statistical errors on this plot are now even at least a factor of 2 better, if not more. And the basic feature that you see here is that we have many dim galaxies and very, very few bright galaxies. Okay? So it's an exponential decline in terms of the numbers of very bright galaxies. Okay, this is a similar plot for the stellar mass function. Okay, the total mass in stars, and that's the evolution of the stellar mass function is what I'm showing on the right-hand side of the plot. So the top, just ignore all the marks and just concentrate on the stars. The top plot is redshift 0 today, and then this is looking at how that stellar mass function evolves back in time. You can see the line here is the redshift 0 function, and so what you can see is that the low mass end is actually way, way lower at high redshift, although the high mass end actually seems to be in place at fairly early times. Even up to 10 gigayears ago, the very high mass end was already in place. Okay.
What are the faint curves on the left-hand plot?
Oh, that's just a set of Gaussians that are fit to that luminosity function. Don't worry about it. Yeah. Okay, so those galaxies are not randomly distributed in space, right? As you saw in one of my first slides, the galaxy distribution is very, very clustered. And this is an animation of the distribution of galaxies in the Sloan Digital Sky Survey. And this also is actually a couple years old. So every point on this plot is a galaxy whose position in redshift space has been measured, so we know its position on the sky. We know its distance from us with some error bar. And from Sloan, we now actually have this well measured over a fifth of the sky on 100 million galaxies with imaging, which is just really phenomenal. And then spectroscopy, meaning we actually have a 3D or a close to 3D position for close to 1 million galaxies. Okay? So one way of characterizing this clustering is something called the two-point correlation function. So if you haven't seen this kind of plot before, I'll just, no, not coming back. Okay, just go through this. So what this plot is just the, on the y-axis, I'm plotting the probability of measuring a pair of galaxies as a function of their separation. So what you can see is that you're much more likely to measure a pair, very nearby you than you are to measure a galaxy very far away. That's basically telling you that galaxies are clustered. And so this is basically a way of characterizing how clustered galaxies are on various scales. And one of the things that you observe in both Sloan and in higher redshift data sets is that this clustering is a function of all kinds of galaxy properties. So I'm showing on the right how this clustering is a function of the luminosity of the galaxy. So very bright galaxies are very much more clustered than dim galaxies. Okay? So it's a strong function of luminosity. It's also a function of color and other properties like that. So the implication of this is, right, so galaxies we think are tracing the underlying dark matter density distribution, but they must be tracing it in a way that is dependent on their properties. Right? They're not all clustered the same. So the bright galaxies must be tracing it in a slightly different way. We characterize that way of tracing it as we call it the bias of the galaxy population. And that bias is basically just the clustering of galaxies compared to the clustering of the underlying mass distribution. Okay? And for these purposes, although it's a function of scale, you can just think of that as what is that clustering on large scales. And so you can see that this is a function of luminosity, right? So the brightest galaxies are the most clustered, the dimmest galaxies are the least clustered. And you can think of an analogy, right? This is basically saying you have more light in the deepest potential wells, and those deep potential wells are themselves more clustered than the less deep potential wells. And that's similar to a mountain range where if you go to Colorado, you see a lot of 14,000 foot peaks. You don't see a lot of them in the middle of nowhere. So those peaks are clustered, and you get more snow on those mountaintops, just like you get more light in these deeper potential wells. Okay, so those are the trends for galaxies. Now it turns out very, very similar trends are observed for dark matter halos. So we looked at the galaxy luminosity function. Now I'm plotting the so-called halo mass function. So this is just like the galaxy luminosity function, which is counting galaxies as a function of their luminosity. Now here I'm just counting dark matter halos as a function of their mass. And you see the same basic behavior, that there's sort of an exponential decline. We have very, very few very high mass halos. So just a few halos more massive than a few times 10 to the 15 in the entire universe. And then lots and lots of smaller halos. Similar trend with halo bias, right? The most massive halos are clustered much, much more than the underlying distribution. And the clustering of those halos is a strong function of their mass. Okay? So now we have just thinking about these two basic statistics, basically the number of things as a function of their mass and the clustering of those things as a function of their mass, can be used to connect to figure out which galaxies live in which dark matter halos. Okay? So as a reminder, here's the halo mass function. If I plot the galaxy mass function or luminosity function on it, it looks like this. Now I've actually shifted this by an arbitrary factor to get them to meet up at a given point, and I'll get back to that point later. So this is the stellar mass function divided by some constant fraction compared with the halo mass function. And there's something sort of immediately obvious, that even though they have these same basic features, a decline here and there's something going on here, right? This is much, much steeper than the halo mass function, and this is also much, much steeper over here. So it's telling you that you can't just have the luminosity of a galaxy proportional to the mass of a halo across the whole mass range. Okay, so we can get another clue then by comparing these two functions, the bias as a function of luminosity and the bias as a function of halo mass. Okay, so I'll talk more about this, but so the missing piece, you can see basically that there is some connection between these two, but it's not totally trivial, right? So this is the missing piece, is basically how galaxies are populating these dark matter halos. Now remember what these dark matter halos look like. The things I was actually plotting in the previous couple slides about halos were so-called distinct halos. So those are halos not including all of their little substructures. Okay, so it's all of the bound objects, but not including all of the substructures. So that's a key point, because the most natural assumption about how galaxies form is sort of what I told you, right? Every galaxy that gets massive enough to be able to cool should have a galaxy at its center. And then those halos merge with each other, so that halos have lots of subhalos. And you don't expect the galaxies to disappear immediately, so you should expect that there should be basically a galaxy in every one of these little subclumps. Okay? So that's the assumption that I'm going to make in this very simplistic galaxy formation model. So I'm going to assume that there is one galaxy in every dark matter halo. Key point is I'm going to include the satellite halos or satellite galaxies. Okay? So I've got two things, one of which I've observed in a simulation and one of which I've observed in the real universe. So a halo mass function or velocity function and a stellar mass function from one of these large surveys, or a luminosity function. And my model is just that basically I take the most massive galaxy and I put it in the most massive halo, and so on down the line by abundance. Okay? Okay? And so the basic idea of this model is just, number one, that galaxies live in halos, and number two, that there's some property of halos that is tightly correlated with some property of the galaxies. So the details of this matter, I call this model the sham because it stands for subhalo abundance matching, but it also is a bit of a sham that you can get all of galaxy formation with 0 to 1 parameters. So the one that I'm referring to is the scatter between whatever property you choose. So some of these details matter, which property, how tightly this correlation works out, and including satellite galaxies properly using the right properties. These details do matter a lot, but the bottom line is that if you take the stellar mass of a galaxy and you match it to the mass or the maximum circular velocity of a dark matter halo for central galaxies, for satellites you have to basically go back to the time when they were central galaxies and match them to that mass, because dark matter halos actually get stripped tidally once they start orbiting a larger system. That model actually pretty much works. So despite its amazing simplicity, with a very few tweaks, this sort of galaxy formation model can describe almost all of the galaxy formation statistics that I've looked at and other people have looked at as well. And I put this in quotes because it's not really a galaxy formation model, right? It can describe them, but that doesn't mean it can explain them, right? But I would claim, and I hope to tell you a little bit about this, that you can extend this model to get real insight into galaxy evolution and the actual physics that's sort of producing this correlation, especially when you combine it with information about the formation histories of halos to be able to connect different epochs. Okay? So here's the basic picture that we get out of this model. Okay? So if you just do this simple approach, you take one property of the observed universe, which is the galaxy stellar mass function, right? Number of galaxies as a function of their stellar mass, and how that stellar mass function evolves. And then I take everything else from a dark matter simulation. Okay, so this is what I get for the connection between the average stellar mass of a galaxy and the average halo mass. Okay, so this is what you see here. This is roughly the mass of the Milky Way. And you see, and now I'm going back in time, so the blue line is redshift 0, the black line is redshift 1, the red line is redshift 2. The higher redshift points are dashed because there's really still pretty big error bars on the stellar mass function, and so I'm much less certain about the details of this, although I think the basic picture is correct. So it's a couple of very interesting things you can see just from looking at this plot that tell you some interesting features of galaxy formation. So the first is that there appears to be this regime sort of roughly for galaxies less massive than the Milky Way, where stellar mass growth is dominating over halo mass growth. So the halos are not growing very much over this time, but the stellar mass is growing. So the galaxies are forming stars even though they're not accreting mass. And the opposite is true at high mass. Those galaxies are still accreting dark matter onto the outskirts of their dark matter halo, but they are not really forming stars. Their galaxies are already in place. There's another interesting thing you can see by looking at the bottom panel. So in the bottom panel, all I've done is taken the y-axis and divided it by the x-axis, and also divided by the universal baryon fraction. So this is the stellar mass divided by the halo mass, divided by the total amount of dark matter that is in baryons. So this is basically telling you what is the integrated efficiency of turning baryons, of turning gas into stars. Okay? And so you see a couple of interesting things from this plot. The first is that the peak here is actually pretty low. Like the best I can possibly do is to turn about 20% of my baryons into stars. Okay? So for some reason, galaxy formation is not a very efficient process, even in the best case. That best case happens at roughly a Milky Way mass, again, and actually peaks at slightly higher masses at earlier times. But the other thing that you see from this plot is that galaxy formation is substantially less efficient at both the high mass end and the low mass end. And you could have already seen that from that sort of comparison plot that we made of the luminosity function and the mass function, right, which just showed you that you don't get galaxies that are as massive as the massive clusters, and you don't get, same thing is true at the low mass end. Okay? So some process, and it may be a combination of many processes, is sort of suppressing galaxy formation at both the high mass end and the low mass end. So either the cooling is being suppressed, there's some extra process providing heating, or the gas, the baryons are blown out of the galaxy, of the halo completely, or for some reason star formation is just not efficient. So any of these things could be going on to produce this, but we now actually can characterize how inefficient it is. And roughly this stellar mass scales as about mass to the squared or cubed power at the low mass end, and much shallower at the high mass end. So the stellar mass scales roughly as mass to the 0.3 power at the high mass end. So we believe this model works, is a pretty good description of the data because it actually reproduces a large number of galaxy statistics. And this is just an example of one set of galaxy statistics that it can reproduce. So I talked to you already about the galaxy correlation function and how that correlation function is a function of both scale and luminosity. It turns out it's also a strong function of redshift. So what I'm showing here, this is essentially, the red points are actually basically the same data that I showed you before. The correlation function of galaxies in the local universe for the 4 panels correspond to 4 different luminosity bins. Okay, so these are the brightest galaxies. These are the dimmest galaxies. You can see that that correlation function is a function of luminosity. It's a function of scale. And the blue line is what we get out of this model. And this is actually the 0 parameter version of the model where we just didn't even include any scatter. So literally just taking the observed luminosity function, pasting it onto galaxies and seeing what comes out. And you can see we reproduce all of these interesting features, including the scale dependence. So at high redshift, that scale dependence is even more visible. So this is at very high redshift, redshifts 4 to 5, as observed from the Subaru telescope. So what you see is that this correlation function, instead of being sort of approximately a power law as it is at low redshift, has this very strong break here. And this break is actually the typical scale of the dark matter halos that are hosting these galaxies. So there's basically 2 terms that come into this correlation function. Remember that we're just counting pairs of galaxies. So you'll have one term which is set by pairs of galaxies that are in the same halo, and then another term that's set by pairs of galaxies that are in different halos. And that actually produces sort of a physical effect in this correlation function, which you can see a little bit for bright galaxies locally and much more strongly at high redshift. So this is just one of the set of statistics that this model is able to reproduce. We've looked at lots of other things. This is 2-point functions. We've looked at 3-point functions. We've looked at galaxy-galaxy lensing. We've looked at the populations of galaxies and clusters. Lots of other things. And you know, the details do matter. And I'm sweeping that under the rug a little bit. But to first order this model with either 0 or 1 parameter describing the scatter, which is pretty small, really works to describe all of this. So now let's sort of take that plot and see what it implies about galaxy evolution. Okay? So in order to make this plot, what I've done is I've taken the connection between galaxies and halos at a given epoch. So I know what that is at, say, redshift 0. I know what it is at redshift 1. And I know on average how halos evolve over that time. I showed you a plot of that earlier. And so I can then use that to connect galaxies at different epochs and see how they build up their stellar mass. Okay, so I know from the simulations how they build up their halo mass. That's shown here in the dotted line. So these 4 panels show 4 different galaxies that end up at different masses at redshift 0. Okay, so this is a low mass galaxy. This is a high mass galaxy in a 10 to the 13 solar mass halo versus 10 to the 11 solar mass halo. And you can see that the dark matter follows this sort of self-similar evolution, but high mass halos actually get more of their mass at late times fractionally than low mass halos. That's a basic feature of hierarchical structure formation. So in any universe with cold dark matter, you will get that basic feature, that small things build up more of their mass fractionally in early times. Late things are still forming basically by the merging and accretion of smaller objects. Okay? So that's a basic feature of cold dark matter. But it turns out that the galaxies appear to be doing something fundamentally different. Right? For galaxies, the opposite is true. For the massive galaxies appear to be already in place at very early times, and the low mass galaxies are still very rapidly forming stars, even though less is happening with their dark matter. Okay? So this is, for a long time, people thought this was sort of a fundamental problem with galaxy formation in cold dark matter, because you have this sort of hierarchical structure formation, and then you have what appears to be sort of anti-hierarchical galaxy formation, in the sense that the massive galaxies build up more of their stellar mass later. And that's actually described quite well in this plot. Astronomers who work on this probably knew these basic things, but this sort of characterizes it in just sort of one slide. So this is the formation redshift. And what I'm plotting here is either the stellar mass or the halo mass. So what you can see from this plot is what is the typical formation time, what is the typical redshift at which I built up either half of my dark matter mass or half of my stellar mass as a function of mass. So the dark matter mass is shown here, right? That's again just comes directly out of the simulation. So the more massive halos, 10 to the 15 solar mass halos, get more of their mass at late times. The low mass halos get more of their mass at early times. And for stars, the opposite is true, even more strongly, actually, that the massive galaxies have built up already half of their mass at redshifts, between 1.5 and 2, and the low mass galaxies are still really pretty rapidly forming. Okay. Okay, so we still need to explain this, but now we can see that this has to be what's happening if we live in a cold dark matter universe. Okay, we can take this same model and look at the formation of stars as a function of stellar mass. And this is a recent result from galaxies in the DEEP survey, actually followed up by sort of an extension of the DEEP called the AEGIS survey, which stands for something extended multi-wavelength survey. I wish I could remember. But anyways, it's a collaboration that basically observed one small piece of sky, a subset of DEEP, in basically all known wavelengths from the radio, infrared, X-ray, with Spitzer, with Chandra. So you can get from that very precise measurements of not only the stellar mass, but also the star formation rate. And one of the very interesting results from from this is that the star formation rate, if you look at the star formation rate as a function of stellar mass, it's a pretty tight sequence. Okay, not all galaxies live on this sequence, but about 2/3 of the galaxies do live on this sequence and have star formation rates which are within a factor of 2 or so at a given stellar mass. And that is true also, this is true more locally, it's true also at redshift 1. And the tightness of this sequence actually doesn't change much, although the overall star formation rate was higher in the early universe. Okay, so in this plot, we've predicted something similar from our model. So this is the star formation rate versus stellar mass. And in fact, the model that I'm presenting here is all analytic, so we're really just talking about average properties of central galaxies. The fact that this is tight means that it probably it's not totally crazy to do this kind of averaging. So this is what we get, right? This is the specific star formation rate, so that's the star formation rate divided by the stellar mass. And this is just the total star formation rate as a function of stellar mass. And the points here are data, and the solid lines here are sort of our favored model. Okay, so the main thing to take away here is that we think this mass to stellar mass connection is tight, and the star formation rate to stellar mass relation is also quite tight. And we sort of have some model that can actually self-consistently describe all of this. So this then shows you taking that one step further to connect it directly to the halo mass. So I can now plot the star formation rate as a function of halo mass in the model. And this plot shows the same data, just plotted differently. So this is the color coding here is now the star formation rate as a function of mass and redshift. Okay? So this is now my basic recipe for galaxy formation. Okay? I know that basically star formation has to be very, very efficient in Milky Way halos, and it has to be very inefficient for very high mass halos and also for very low mass halos. And I also know that the global efficiency has to increase quite rapidly as I go farther back in time. So this plot is really even more instructive if you think about how does a typical galaxy evolve as a function of mass and redshift. And this is what I'm showing here. So these black lines just show some typical galaxy trajectories for galaxies that end up at different masses at the present. So a galaxy that ends up as the central galaxy in a massive halo today started out in this sort of very, very rapidly star-forming region at early times. And then this is its typical trajectory. At some point, basically, its star formation was shut off by some process, and it ends up here, having formed most of its stars quite early on. Whereas a low-mass galaxy, so for example, a dwarf galaxy in the field, sort of always spent its time in this very inefficient region. So it just, even though it was accreting dark matter, its stars were just sort of piddling along very, very slowly, very, very efficiently over this time. So this plot I find very instructive to sort of understand these sort of basic trends in galaxy formation, right? The massive halos host more massive galaxies. They spent more of their time in the region where they were rapidly forming stars. But that happened largely at early times, right? Whereas for low-mass galaxies, they're just sort of starting to get a little bit more efficient today. And it turns out that this sort of region, remember we talked about how galaxies appear to have bimodal properties in a lot of different properties. So this shows their star formation rate as a function of stellar mass. This shows their surface brightness as a function of stellar mass. These are observations from Sloan Digital Sky Survey. And this transition appears to happen for galaxies at a stellar mass of about 3 × 10⁻⁻10 solar masses. And that basically corresponds exactly to this mass where you sort of start turning off star formation. This sort of corresponds, that transition corresponds to this sort of more efficient peak. And I won't have time to go through all of the possible physical processes that can be doing this, but schematically, the few of the possibilities basically are that at high mass, there's lots of different things that can go on. You can basically have some sort of inefficient cooling. You can have something that heats the gas. So a popular candidate is that we expect every galaxy has a black hole at its center at some point that is an active galactic nuclei, which basically injects energy into the gas and slows down the cooling, basically making galaxy formation inefficient there. At low mass, a popular candidate is supernova feedback. So the basic idea is that you have some number of supernovae. In low mass galaxies, you have a much more shallow potential well, and so that a fixed amount of feedback will be much more efficient at actually heating the gas and even blowing the gas completely out of the galaxy. And so that's one of the basic ideas. But there are several others. And at the very low mass end, we expect that very low mass galaxies actually, if they are affected by the reionization of the universe. If they're not massive enough to basically hold on to their gas, then when the universe reionizes, all of their gas can be blown out. So that's just a schematic picture. What we're working on now is really understanding. We now actually can characterize this connection tightly enough, and actually with real error bars, that we're starting to try to put real constraints on these various properties, because they actually do impact in slightly different ways as a function of time. So I will just end there and sort of try to summarize what I've gone through. So just the basic picture is that you should realize that sort of our current understanding of lambda CDM is now we really have the basic parameters of this model pinned down to quite high precision, and that means we really do know how structure evolved in the universe. It's a computationally difficult problem, but it's conceptually not so difficult anymore. And because we now have these large galaxy surveys, which are still ongoing, there'll be really very exciting surveys over the next decade, that really characterizes the galaxy abundance and clustering over the last 10 billion years or so. And basically, we have a framework for connecting these two populations. So a few of the lessons that I've learned from this, one is that mass really appears to be the dominant, halo mass appears to be the dominant thing that's setting galaxy properties. Whatever it is that's setting galaxy properties appears to be very tightly correlated with halo mass. Now, it could be that it's really the mass accretion rate, which is also tightly correlated with halo mass. That's the fundamental physical process. And understanding really what teasing out these fundamental processes is one of ongoing research. But to zeroth order, galaxies are actually a one-dimensional family. The scatter is very, very interesting and one of the most active topics. But to zeroth order, massive galaxies are red, form their galaxies early, are bulgy, didn't have very recent major mergers, don't have ongoing star formation, and vice versa. And a lot of the scatter in stellar mass at a given halo mass can actually just be explained by scatter in mass accretion histories for a given halo mass. The second lesson is that galaxy formation is inefficient, even in the best case. The best case is roughly Milky Way halos, and it's way less efficient at higher masses and lower masses. And then a third thing is that although you have this situation where dark matter halos form hierarchically, and galaxies have sort of the opposite effect, that large galaxies form their stars first and small galaxies form later. That's often called downsizing. That's really a natural outcome of basically taking halo accretion histories and putting in inefficient galaxy formation at low mass and high mass. Okay? There's no sort of fundamental problem with producing that. And lots of open questions, right, distinguishing between the various physical processes that cause these scaling relations. And I think the data is now really getting good enough that we can do this, and this kind of approach really provides some insight. And then really understanding the scatter and what it's due to, and what is the fundamental physical processes. Thanks. Thank you. We have time for questions.
Yes, thank you. Incredible talk, actually. And before I ask my question, I want to acknowledge Pierre Schwob sitting here in the front, who is an extraordinarily generous donor both to the SETI Institute and to the Kavli Institute at Stanford, and helps make both our work and your work possible. My question to you would be, this field is so rich with the difference between, or the combination of theory, numeric modeling, and observational data. If you were to invent the next instrument that would give you the best next step forward, what would it be and what would that data look like?
Oh man, you're really putting
And keep
me
it to
on
2
the
minutes.
spot here. Yeah, I mean, it's difficult to choose. As the director of our institute knows, he's currently sitting on this decadal survey, which is tasked with making this choice. I mean, there are a couple of things that, I mean, there are basically 3 frontiers that, that I think are really exciting. One is the fact that, doing these very, very large surveys, largely from the ground, that will really get us statistics in a way that you can't do from, from very targeted observations. I think that's a very exciting frontier. Another thing that's really going to be new and is, more related to things people here are working on is studying the gas, right? Which largely can be done with 21 centimeter, with radio observations, and that's an incredibly exciting frontier. I didn't talk about the gas at all today, but obviously that comes into the picture. You can't form stars without gas, and it's very exciting. That some of the surveys, including things like the Allen Telescope Array, which people here are involved in, will be able to actually trace out the gas over these same things, so that we need to put all of those pieces together. And then the third thing, of course, is being able to do very deep observations from space, including in the infrared, which will actually, one of the biggest uncertainties in what I told you about here is really what is the stellar mass and the star formation rate. I didn't talk about the uncertainties in that at all, but those uncertainties are big. And in fact, the biggest uncertainty in the connection that I talked to you about now, observationally, is actually, for a given galaxy, what is its stellar mass? It's actually the biggest uncertainty. And what you really need for that is detailed multi-wavelength data, right, to really pin those things down. So,
Thank you.
As you know, there's sort of an idea, people talk about the cosmic web, where there's almost like a Voronoi tessellation of space, and clusters are the nodes and so on, and people say voids are fundamental and stuff like that. So a 2-part question. One, do the simulations that you showed validate that picture at all? And to what extent does any of that affect the kind of work you're talking about?
It's the fundamental basis of everything I talked about, right? If you look at these pictures, let's see. This is a good one, or this one, right? I mean, this is the cosmic web, right? That picture came from exactly these kinds of simulations, and really was validated once we started to do, large galaxy surveys that start to trace this out. But I would claim there's actually, there is a fair bit of controversy in the modeling in sort of what happens in the voids. But I actually think that's a detail. I think to 0th order, this model where you basically have a galaxy in every dark matter clump, tracing exactly this web, matches all of the data. It really matches almost all of the statistics that we've looked at. And it's an incredible validation of lambda CDM. I mean, there's tons of details that this actually does validate, including the clustering of clusters, where galaxies sit in underdense and dense regions. It's true that actually the extremes of the distribution in environment, clusters in the voids, provide some of the most stringent tests on the model. And there are some challenges. I think that understanding galaxy formation in low density regions is a big problem. But I don't think there's been any sort of fundamental issue that that the structure has not been able to explain, at least to 0th order.
Yeah, first I wanted to say thank you to Tom. That was totally unnecessary. and Risa, I feel like a superluminal traveler. The density of your talk was so extraordinary. But I do have a question about AGN. How well do we understand the regulating the effect of AGN on galaxy formation?
It's a huge and very active and very controversial topic. And I would say not very well, although a lot better than we did a few years ago. I think we know that it's important. It's really not clear, even though we know that AGN exists and we know that they're inputting energy into the gas. It's actually, the details of how that happens are quite unclear, and most people doing detailed simulations to try to model this. It's challenging to try to, even when you have the energy, to try to get that energy into the gas in a way so that it affects galaxy formation in the way that we think happens. So there are other competing processes that could also be important. Gravitational heating is one. The effect of magnetic fields is another that's really understudied and actually may be more important than people have understood. And yeah, so it's an active area. I think there's lots to do there.
What kind of observational data do you currently have to map the dark matter distribution? How does the resolution for that compare to the resolution of things like the Sloan Digital Sky Survey?
Actually, I didn't quite understand when you said resolution what you're referring to.
Spatial resolution.
Of which data?
The data that you're using to get maps of dark matter distribution.
Oh, okay. Okay, right. So that's a two-part, depending on whether we're talking about theory or observations.
Yeah, observation.
So in terms of, right, so I talked about a very, very simple mapping, which was basically just counting, right? But the reason we believe it works is because we've looked at all kinds of other things, including the clustering and lensing data. So, weak lensing is basically one of the best ways to map out the dark matter distribution. Basically, what's done there is, you're measuring the positions of galaxies and looking at statistically how their light is distorted, right? And I don't know, so that data is exactly, I'm not sure how to compare the two resolutions you were talking about, because those data come exactly from these same surveys, right? So the best data we have locally comes from the Sloan Digital Sky Survey. At higher redshift, there's, for example, the Cosmos survey, which can do this. But those data, sort of statistically, they're not at the level that the simulations are now, but they're certainly rapidly improving.
Is there, I guess, a correlation or expected correlation between the dark energy and clustering and dark matter and basic matter? And is there a plan for how to detect this and map it out?
Yeah, great question. And if you have me back some other time, I'll talk to you about dark energy. But as far as we know, dark energy is smoothly distributed throughout space. So if dark energy is a cosmological constant, then that means it's basically a smooth property of space. So it's the same everywhere. It's a fundamental property of space. So it does not cluster in the same way that dark matter does. And we know for certain that it doesn't cluster like dark matter does, because we would have observed that if it does. If it deviates from a cosmological constant, if it's not sort of this simple picture, one number that's always constant in time, if it varies with time, it will also vary with space. But that has to be pretty moderate. It can't be very strong, and it has to be fairly smooth. That variation has to be on pretty large scales. So there are a couple of ways to trace this out, but basically what you're trying to do is to look. So dark energy affects two things. One is the expansion rate of the universe, and the other is the evolution of structure. Right? So it's exactly the things that I've been talking about here. So if you do a very, very large galaxy survey and use galaxies as basically the tracers of the structure, as long as you understand that tracer, then you can actually measure what is the impact of dark energy on very large scales. Exactly. People are actively working on this. There are current constraints, both from Sloan, from what you actually want sort of the largest lever arm possible in terms of, in terms of how much time you're looking over, because you want to measure, the expansion rate over a large time and the clustering over a large time. So for just measuring the expansion rate, supernovae are one of the best ways, and that was sort of the initial detection of the acceleration was done from supernova. Those basically trace the expansion history of the universe. But a complementary technique comes from actually tracing the structure. And some of the strongest constraints come from basically looking at the clustering of galaxies today, or actually also the clustering of clusters, basically, because those are more sensitive. You saw that exponential dependence. That actually means there's sort of a lot of dependence on what the dark energy properties are. Comparing those to the CMB. So you basically want to compare, in this very simple lambda CDM model, I know exactly if I have these CMB measurements, what the number of clusters should be as a function of mass. So if I go out and measure those and they differ from the lambda CDM prediction, then that means that there's possibly some deviation. So that work is ongoing, but I'm for example involved in something called the Dark Energy Survey, which is going to be a galaxy survey of 5,000 square degrees, several magnitudes fainter than Sloan, which this is the main goal of that survey, and it's a huge area of work for the next decade.
In your first animation, you had the universe rotating, and I think that was just an artifice so that we can sense the three-dimensional structure.
Right.
But indeed, there is angular momentum in the universe because every galaxy has some. And angular momentum, of course, affects very greatly formation processes, as we see particularly in planetary systems. Do you take that into account? And have you given thought to how to include angular momentum in?
Yeah, so that's a great question. I completely ignored angular momentum, and it clearly is very, very important for forming galaxies. It's basically the reason that we think we have disk galaxies at all. So we think that most angular momentum in galaxies is basically generated from tidal torques in the early universe. And galaxies are basically spun up by a series of mergers. So we can study this process quite accurately with these kind of dark matter simulations. I've written several papers on that, actually. And we know what the angular momentum distribution of the dark matter is in simulations. But it's actually much harder to understand the angular momentum distribution of the gas. For a long time, people sort of assumed they were the same. I'm pretty sure that is not true at all. And but it's sensitive to all of these complicated feedback processes that I talked about. So I think there's a couple of interesting things. I mean, the first is that the fact that this very simple model works and this correlation is tight means that angular momentum can't be the dominant thing, right? Mass is definitely dominant over angular momentum. But I think it's very likely that angular momentum is the next parameter or the second next parameter that's important in setting the scatter and in determining the shapes of galaxies and their sizes. And understanding, I mean, this is a very active area of research. I work on it as well, but understanding galaxy sizes is not really a solved problem. But it's all about basically understanding the relation between the angular momentum of the dark matter and the angular momentum of the gas.
Thank you very much.